Okay, non-uniform circular acceleration, which means that the speed is going to change. So there's going to be a speed. So in this case, you're speeding up and then slowing down and then slowing down further, speeding up. So in this sort of motion, the acceleration is not uniform. It's going to be non-uniform. Right, the formula is going to look the same, except now you may have some multiple forces acting on the system. Instead of a single force, you can have multiple forces. So how do we do the calculation if that's the case? So non-uniform acceleration, which means that the speed is going to keep changing. Ooh. And we may have multiple forces acting on a system. All right, so right here, imagine that this thing is moving sideways. And right at that point, it's going to have two forces acting on it. It's going to have weight in the downward direction. There's going to be a normal force in the upward direction. And then eventually this thing is going to start to climb up. It's going to go up, and it's going to go up, and then it's going to come back down. All right, so the speed is going to diminish. Speed is going to become even smaller. And then it's going to pick up speed. And then obviously it's going to have the maximum speed at the bottom. Okay, so this is non-uniform circular motion. All right, so in terms of topics, this is going to be non-uniform circular motion. Non-uniform circular motion. All right, now we got a problem. The problem is, notice that you got two forces acting on it. One force is in the upward direction, the other one is going to be in the downward direction. Here, the weight is going to be in the downward direction. Weight didn't change. And there's also going to be a normal force in the downward direction. Here, the weight is still the same. It's in the downward direction and is going to be to the side. Okay. So how do you know what the centripetal force is? When you have multiple forces acting, how do you know what the net force is on the radial direction? Here's how you do it, guys. If it looks like this, if you have one force in the downward direction, if you have a second force in the upward direction, when you look at the net centripetal force, if the force is to the center, it's going to be positive. If it's away from the center, it's going to be negative. F2 is going to be positive. F1 is going to be negative. All right, so if the force is directed towards the center, it's going to be positive. If it's directed away from the center, it's going to be negative. All right, so if that's the case, let's take a look at the forces here. All right, so let's take a look at that case. Look at the centripetal force in this case. So N is going to be directed towards the center, so this is going to be positive. W is directed away from the center, so this is going to be negative. All right, so this represents this case. All right, so that's that. Got it? All right, so now let's take a look at this case. Let's take a look at the net centripetal force. W is down, it's pointing towards the center, so this is going to be positive. N is down, directed towards the center, so this is also going to be positive. So both of them are directed towards the center. So if it's directed towards the center, W is going to be positive, N is going to be positive. All right, so it's that case that you're looking at. All right, so the net force means that you're summing up all the forces. All right, take a look at this. F is directed towards the center, right? So this one is going to be positive. Mg is pointing away from the center, so this is going to be negative. F here is pointing towards the center, it's going to be positive. Mg is pointing towards the center, so it's going to be positive. F here is pointing towards the center, so it's going to be positive. How about Mg? Is it positive or negative? So Mg, is it positive or negative? You guys are thinking that this is going to be negative or positive regardless. It's not a centripetal force, guys. This doesn't have a component in the direction of the center. All right, so this doesn't have a component. So this does not contribute to motion. F here is going to be positive. Mg here is not a centripetal force, so it doesn't add into the equation. Okay. Now we're ready to solve this problem.
Again, according to plan, as they leapt off the bridge while tethered to the cable.
Stand up. Give it on three, go. On three, double. One, two, three, go.
But as the team was about to reach the end of their first arc, the cable.
So what do we have? We got like five people.
Snapped.
Approximate weight 900 pounds. So what's the amount of tension that they induced on the cable while they were going at 78 miles per hour? So what is
1, 2, 3, go.
But as the team was about to reach the end of their first arc,
right at that moment, what's the amount of tension that these guys are inducing on the cable? So what do you have? These guys have weight. It's going to be in the downward direction. They are inducing tension on the cable, so that's a reaction force. These people are moving sideways. Right, so these guys are moving sideways in this direction. And then the motion is kind of like this. It's project. Right, that's the motion that we're looking at. So the question is, what is the amount of tension that they induce on the cable? So I'm going to put a question mark here. And so we need this in terms of newtons, and then what we need to do is we need to convert this to pounds. All right, so the question is, did they get the wrong cable? All right, so that's the problem that we will focus on. Did they get the wrong cable? All right, so this is problem number 6. Problem number 6, formatted solution sheet. All right, so let's just draw this out. These guys are doing a pendulum move. Here's the length of the cable. All right, they pivoted right here, so they do a pendulum move. And right at the bottom, these guys are going sideways. All right, so here's the cable. Okay, so let's draw the forces. They got weight in this direction, and they induce a tension on this cable in the opposite direction. This is the tension. And these guys are moving sideways at 80 miles per hour. Okay, so that's the number that we will get to use. Cable is 200 meters long, 200 feet long. All right, so speed is 80 miles per hour. R is 200 feet. And the estimated weight of these people, 900 pounds. Okay, so I need a bunch of stuff from you guys. Miles per hour to meters per second, so I need that number. 200 feet, we need this in terms of meters. And obviously, we need this in terms of newtons, 900 pounds. Okay, so whenever you guys get a chance to just work on those numbers. All right, so this is a centripetal circular motion, this part of it. All right, so we're just focusing on a small arc of it at this point. So we're interested in the tension that this motion is going to induce. So what is the maximum tension that they're going to induce on the cable? And then express this in terms of pounds, and then compare it to the tolerance of the cable. The tolerance of the cable is going to be 4,000 pounds. All right, so the maximum tolerance of this cable. So these guys end up picking a cable for themselves. It's able to tolerate up to 4,000 pounds. All right, so this is the tolerance of this cable. All right, so this cable has a tolerance which is 4,000 pounds. Okay, so what that means is if they exceed that 4,000, if T exceeds this tolerance, this thing is going to snap. That's what it means. So the question is, did it snap? All right, I got a bunch of numbers from you guys as I was storytelling. All right, so 80 miles per hour is going to be 35.71 meters per second. So give yourself 5 points for that one, Patricia. Chantel, and those of you guys who got 60.97 meters, give yourselves 5 points for that one. And for 900 pounds, we end up getting 4,090.9. Okay, so I'm going to show you something. I'm sure you guys noticed it by now because you've been using it. Weight is mg, right? So g is roughly about 10. So if you move the decimal to the left, that's going to give us our mass. All right, so in this case, the total mass is going to be about 400 kilograms. Okay, so I think we got everything that we need. All right. It looks like a complicated problem, but it's not. This direction, and the y-axis is going to be our radial axis. Okay, so this is going to be my radial axis. It's going to be pointing in the upward direction. Okay, so now let's take a look at the centripetal force on the y direction, or we call it the radial force, but I'm going to use C instead of R. So T is up, W is down, and the net centripetal force is going to give me this m times this centripetal acceleration, which is v squared divided by r. All right, so I'm looking for T. All right, so which means that I'm going to add W to both sides. All right. All right, so what happens is W is going to cancel, add up to 0 more like it on the left hand side. So now I got an expression for T. All right, so the tension on the cable is going to depend on the weight. All right, so that's common sense. Heavier you are, the more the tension that you will induce on the cable. So we got that. It's also going to depend on your speed as it so happens. Okay, so speed becomes a variable. So I'm just going to stop at this point. A couple of things that I need to emphasize. And all of them are commonsensical at this point. All right, so for a given speed, the only other factor that matters is this. For a given weight, the only other thing that matters is the speed. All right, so the larger the speed is, the larger the tension is going to be. So we kind of expected that. What else? Smaller the speed is, smaller the tension is going to be. Okay, if there's no speed, if this is 0, tension only depends on the weight. As soon as you start to move, tension changes. Tension is going to go up. All right, so the motion is just going to increase the tension. So we kind of expected that. So what is the tension when these guys are moving at 80 miles per hour? So what is the tension that these people will induce on the cable? And if this tension exceeds the maximum tolerance, this cable is going to snap. Okay, so we kind of knew that. So let's check to see if that's the case. So we got a bunch of numbers, so we'll use the numbers. So the weight is going to be 4,090. So this is 4,090 point, what is it, 9? Plus the mass is going to be 409.1. And these guys are just going at what speed? 80 miles per hour, so it's going to be 35.71 square. And everything is going to be divided by R. R is going to be 6.97. Okay, so that's a 60.97. Okay, so Lucia, give yourself 5 points for that one. I think that, okay, hold on. That's the previous number. Okay, let's get 490.9 plus the other number. So in terms of newtons, it's probably going to be about 12,000. Okay, very good. So it's 12,690, 644, 695, 673. Not a single person gets the same number. 647. Okay, 647. Whatever, whoever, you guys came up with 12,000 something. Okay, 647 is, I'm going to go with this one for now because I'm looking at the numbers. Most of you guys are around that. So 12,000 something, give yourself 5 points. All right, the only thing I'm interested in is this number in terms of pounds. Okay, so depending upon if you're using your cell phones or real calculators, the numbers kind of jumped around a little bit, but that's fine. Okay, so most of you guys converged to 12,647. Okay. All right, so the next thing I want you to do is just convert it to pounds so that we can actually do some kind of a, all right, so conclusion out of that. So 10 pounds, roughly about 10 pounds is, no, 2.2 pounds is roughly about 2,800, almost. Okay, so I'm just going to wiggle this. I think this is correct. All right, so the tension that these people induced on the cable is about 2,800. Yeah, it is 2,800 roughly pounds. You know that 2,800 pounds is less than 400. It's going to be less than 4,000 pounds, right? So that's going to be less than 4,000 pounds. All right, so immediately you know, let's paste this. All right, so which means that the tolerance is still larger than this is still larger than the maximum tension that they induced on the cable, which means that the cable did not snap.